Hi! In this series, I'll be going through a basic course on the row analysis and maybe supplement your understanding about what row analysis is. So before we can talk about row analysis and analysis in general, let's talk about the real numbers since that's what we'll be studying. And so a real numbers can be described as a complete ordered view, and we'll go into what this complete ordered view means. So to start off, let's start with what a view is. And a view is a set with two binary operations with addition and multiplication. So just think that whatever you have learned from your preschool days to now, to your maybe to where you are now, you know how the real numbers work. You know that 2.5 plus 3.5 equals to 6. You know 5 over 2 is a rational number. You know that 2 plus 3 is still an integer. So you just need to remember that fields have a general field has this addition and multiplication as well, and they satisfy these axioms that are actually what we already know to be for a real number system that we have done in any calculus course or anything before that. But we are really diving right into the basics and expanding on it to understand what are real numbers. And so the axioms for addition allows it to become a abelian group, and the axiom for multiplication makes it an abelian group as well. And together they form a commutative ring basically. And these terms are just terminology in algebra courses, but basically you just need to know that whatever you had understood about the real number system, the properties of the fields are almost similar with certain properties that only real numbers have basically, which makes it special. But most of the fields have the common addition axioms where it has an inverse. It contains the identity 0. It's commutative, associative, as well for multiplication. And one thing that puts fields different is because with the two binary operations, it comes with the distributive laws. So they relates the two operations together. And so some examples of field that you might have already known are the field of rational numbers, the real numbers, the complex numbers. And fields can also be finite, such as the field of 0 and 1, which is actually just the congruence classes of Z mod 2. So it's written usually like this, or you can just write it like this. Some non-examples of fields are natural numbers and integers, because for the multiplication there does not exist an inverse that is still an integer or natural number, and so it doesn't hold true. And really what happens is that we have a natural number system and we build the integers by introducing the inverses, and then we build the rational numbers by introducing equivalence classes. And from the rational numbers, it's how we're gonna build our real number system, basically, and all other ordered fields. But we'll get into that in the next few videos. So now that you understood what a field is, we can see that there are certain propositions that are very common. And so if we let two elements be inside F and they add together to remain the same, so let's say Z plus A equals to A, then Z has to be 0. And so this shows the uniqueness of the additive identity. And all the proofs can be found in the textbook, which I'm using is the Bartley and Schaubert textbook. I've also put in a bit of Rudin just to, if whoever wants to use Rudin for more practice. So I'm mixing the two and trying to give you a complete picture about row analysis basically. So with that, there will be another theorem that says that if A times B is 0, then either A or B is 0. And this is important, so I shall just give a small proof. So you let A and B equals to 0, and you suppose one of them is non-zero. Because this is non-zero, there will exist an inverse. And so you just multiply the inverse and you just get B equals to 0. So the proofs are very simple because you have an understanding of how to play with the real numbers already. And these properties just is to verify what we've normally understood. So now the thing is, why is it that there is these real numbers in the first place? And how do you know that not all the real numbers are rational numbers? So we need to show that there will be at least a real number, because this is not by showing that does not exist a rational number. And you can read the proof about why there does not exist a rational number such that r squared equals to 2. And that's because if you were to write r as p over q, when you square it and bring over, is p squared equals to 2q squared. And so this means that p squared is even. And if p squared is even, it implies that p is even. And so you can replace p with 2m and see that now q is even. And so this shows that the hypothesis where p over q squared equals to 2 will lead to a contradictory conclusion, because now q and p have a common factor, which is 2. So it means that does not exist a rational number such that r squared equals to 2. And because of this, we see what Rudin has says, and this shows that the rational numbers have certain gaps in them. And despite that there are always a rational number between any two, the real number system will fill in these gaps. And that's what we're really trying to study when we do real analysis. So that's all for fields. So now we got to talk about the second thing, which is the order. So it's a complete order field. So now we'll talk about what does it mean to be ordered. And so an ordering doesn't just apply to field, but it actually can be placed on any set, so a random set. And so an order is a relation that satisfies these properties. And this is really what is actually known as a total order. There's something known as a partial order, but for fields we only deal with total order, so it doesn't matter. And so for total order, it means that when you have two elements in the set, you must be able to compare them. So it's either one is less than the other, so all of them are related basically. And there's the transitive property as well. So if x is less than y and y is less than z, then x is less than z. This less than might not be the less than that we usually define in real numbers when you deal with a random set. But for real numbers, this less than means y minus x is positive. So that's what it really means. And so if you do this for every single element in the set, then you have defined an order in the set. And so for an ordered field, more specifically, not only does it have to be an ordered set, meaning the order has these properties, because it has a few operations, we want it to be respect these few operations. And so if x plus y is less than x plus z, then y is less than z. And if both are positive, so x is larger than 0 and y is positive, then x times y will still be positive. And this shows that Q is an ordered field because we know this holds true in the rational numbers. And it also shows that the real numbers that we think of is an ordered field. And the familiar rules that we play with will stay the same. And so I won't go through the proof of this. But what I'd like to take note is that x squared will always be positive in this case. And really it's because of this property definition of an ordered field. And so this means that 1 is positive. And if 1 is positive, n is also positive for any natural number. And so you can really, what it means is that you can put the natural numbers as a subfield of Z. N is not a subfield, but you can do an inclusion into Z. And this Z can do an inclusion into Q. And it also means that Q can include into R. So there is a canonical inclusion into of NZ and Q into any ordered field. And so this is what it means when Rudin defines Q as a subfield of any ordered field. And because of this, it means that the ordered fields are infinite and it cannot be algebraically closed. Because this x squared plus 1 has no solution in an ordered field. Because x squared needs to be greater than 0. And as a result, we don't really need to worry too much because these properties are all things that we have been taught since we're very young. I'm just expanding on a more general case now that we don't really deal with just the real numbers. And so, the last thing we need to finish for this video is to complete the definition given by Bertley and Schaubert, which is what it means to be complete. And before that, let's define some notions. So we say that a subset is bounded above when there exists a number in the set such that every element in the subset is less than this U. And that's called an upper bound. And the lower bound is every element is greater than the U. And it's bounded if it's both bounded above and below. And so, we see that the set x less than 2 is bounded above and the number 2 or any number greater is an upper bound. So as long as you have one upper bound, anything greater than that, you can just keep adding ones. So upper bounds are not unique in this sense. So if it has one upper bound, it has infinitely many upper bounds. But because of that, what we really want to care about is the least upper bound and the greatest lower bound. And so this is a special element, and so we call it the supremum, or also known as the least upper bound. And it satisfies the condition that it is an upper bound first of all. And if you were any upper bound, then you have to be greater than this least upper bound. A same definition follows for infimum, which I'll leave you to read. And it is quite clear that because it is the least and the other one is the greatest, it is unique. And so we see that because it's unique, we give it a special notation and is known as the sup of the subset and the inf s. So I hope this is clear on what the definition is for a supremum and an infimum. We'll be playing with this definition a lot in real analysis because many of times when we have a limit of a sequence, it will be the supremum or a limit of a set. And we'll see more in the subsequent videos. But first you must understand what it means to be a supremum and what it means to be an infimum. And we can see that in a set such as this, where it runs over real numbers, where x squared is less than 2, it has the least upper bound of x being square root 2. But if we were to take into the context of the elements in the rational numbers, then it cannot have a least upper bound. Because this least upper bound has to be square root 2, and this is not a rational number. And so, when we're talking about least upper bound, it must imply that it is in the larger set. Basically the ambient set, your parent set, that you take a subset of. And so, it may or may not exist. And one thing to note is that an ordered set has this completeness property, or known as the least upper bound property, is that if any subset you take that is bounded above has a least upper bound, then it is complete. And so what it means to say now is that the real numbers is a complete ordered field. This complete, it comes from this least upper bound property. And so we can see that the natural numbers is complete because let's just say you have a natural numbers over here. So 0, 1, 2, and then you just take a subset. So this is n. We can see the least upper bound is clearly n because anything n is the greatest number such that everything below is less than it. And because of that, we can also see that the integers is, when bounded above, any subset has a least upper bound. And what we have defined earlier and described the real numbers is a complete ordered field. And so the real numbers, of course, it has this least upper bound property. And lastly, one non-example will of course be the rational numbers, because we can take this subset and see it doesn't have a least upper bound. And what is interesting is that based on our construction of the real numbers and how we have given it the least upper bound property, it can be shown that it is any other ordered field that has the least upper bound property is isomorphic, meaning you can just translate it back into the real number system. And so the real number system can be taken as the only ordered field with the least upper bound property. So whenever Bernie and Schauer talks about real numbers, it's really because he wants to use this least upper bound property. But there are certain cases where it can apply in a general context, and we don't really need the least upper bound property to help us. And I'll show you how when I'm doing my subsequent videos. So I'll extract out when you are using the least upper bound property and when you don't, so that you have a better understanding of this real number system. So I hope you have enjoyed my video, an introduction into real analysis. Thank you for listening, and I'll see you again. Bye.